primary loop alone function in that perspective was just studied in the earlier classes, taking case study of load change in area, only one area, load change in second area, and load change in both the areas when there will be a change in loads of area 1, area 2. There were small changes in the equation. If I go back to the load change in area 1, the important equations were change in frequency deviation or delta omega or delta F. How is that? And what is that actual tie line power flow occur among them as another equation. These two equations are very important in solving the problem. We have seen when we were working upon the problem and understanding the problem nature and how to compute with them. When the change in load area 2 is experienced, similar work with the opposite domain was worked out, and we could see the change in frequency deviation delta omega what we got in the first case study is similarly minus delta PL2 change in areas load 2 divided by 1 by R1 plus D1 1 by R2 plus D2 that we called as area frequency composite response. That's what we have mentioned here. 1 by R1 D1, 1 by R2 D2 were replaced as beta 1, beta 2. And numerator we had step change in load like our step change in load in the first area. Then what is that exchange among the corporations A and B are 1 and 2 areas? This was what the minus delta PL1, the change in load into beta 2. Beta 2 means composite frequency response from second area divided by responses beta 1, beta 2 in the denominator. The same way we'll have frequency deviation delta PL2 change in load in area 2 beta 1 plus beta 2 and the exchanged power among the corporation being delta PL2 step change in the load. See the minus here, minus has gone. So beta 1 the composite response of opposite area. We are experiencing a change in load area 2. The opposite frequency response composite is beta 1 divided by beta 1 plus beta. There is a similarity between this equation and this equation. With the step change in load 2 area, minus is taken out. Step change in load area 1, there is a minus visualized. And of course, we know delta P12 is same as delta P1 negative. It means there is a negative sign shows opposite to each other. So these were the two changed equation from area 1 perspective. When the same was viewed, the load change in both the areas, how we can write balance equations in the area 1, area 2, like this area. Balance at this point, balance at this point means power balance. What is this PM1, PL1 and minus P12 and what is this delta omega into 1 by R1? The same thing I can write here. The same thing if I rewrite here, I can simplify. I will get the response. One is the deviation frequency is just see the numerator minus outside step change in load in area 1 step change in load in area 2 divided by composite frequency responses of area 1, area 2. Then the net power exchanged among them using one of the equation, either this equation or this equation, I can simplify for delta P12. When I use second equation, I referred second equation here and I mentioned with the arrow here. What is that delta P12? If I substitute what is delta PM2, what is delta PL2 after transferring other side, I can get this equation. Once I simplify, I can make either this kind of notation, which is delta PL1 beta 2 divided by beta 1 plus beta 2. This is the power transferred from first area's perspective, power change in second area perspective like that. I can add it, that become net exchange among the areas. Or I can simplify as beta 1 plus beta 2 in the denominator if I take out and make some simplification. These were used in the numerical solutions. Then in line with this, one simple problem we began in the earlier class with the two areas and base was given how that the frequency deviation, how that talent for flow we have just understood. And similarly, we continued the particular mechanical power or pickup of the power from area 1, area 2 like that. Okay. Okay, someone is trying to enter. Just I'm blocking it. Okay, that's all. Next one. And we have seen another numerical problem. Hope I'm audible to you all.
Yes, sir.
Please, thank you. This is another problem we have visualized with the area 1, area 2 perspective, R1, D1, and how beta 1 can be quantified from that, R2, D2, beta 2 can be quantified, how we can find out frequency deviation and exchange of power among them we can get. This was already seen in the earlier class. Now today I wanted to discuss one more problem which is not seen in the last class. Okay, I read it out. A 2000 megawatt control area 1 is interconnected with 10,000 megawatt area 2. The 2000 megawatt area has the system parameters as the area 1's response characteristics. R is 2 hertz per pu megawatt, and the area's load damping constant D is 0.01 pu megawatt per hertz. So just see R and D of first area 2000 megawatt area is given. Now look at the comment. Area 2 has the same parameter. R and D are similar by number, but on a base of 10,000 megawatt. So this kind of questions you are sure to experience in the exam. Instead of telling you R1 D1 of area 1, R2 D2 of area 2, what might be the logic? R and D they may mention these are referred to area 1 with respect to certain base of that area, and with respect to area 2 similar values to be referred on base of said value of that area. So then these became R and D in general. R I should get into R1, D I should get into D1. From the same R and D, from the base value or capacity value of the area 2, I should convert it to R2 and D2. That's what I am going to present you in this representation. So area 2 has the same parameter, but on a base of 10,000 megawatt. A 20 megawatt load increase takes place in area 1. See, the change in load is in area 1 by 20 megawatt. Find static frequency drop and tie line power change. It means delta omega or delta F is of the need, and tie line power change delta P12 is of requirement. Here they have not asked what is the steady state frequency after the load. It means F1, F0 is the basic frequency, F1 that is not asked. Mostly F is not mentioned as a 50 or a 60 hertz or even 1 pu like that, not mentioned. Hence they are simply asking deviation. If you have been given the frequency as a 50, there could be a chance that what is the revised frequency of operation would be asked. Then let's see here again 2000 megawatt based reference they are mentioned. Then hidden base of the system here is 2000. Can you see here? Then let us take 2000 megawatt as a base power and let us compute what is R1, what is D1 for that. Let's see. Beta 1 is 1 by R1. R is put here 1 by 2 plus D of 0.01, which works as 0.51 pu megawatt hertz per hertz. This is the composite frequency response from area 1, nothing but 1 by R1 plus D1. So these were referred as base of 2000. Hence they were copied directly as R1, D1, and B1 remain, beta 1 remained as 1 by R1 plus D1. Now, when you want to convert them to beta 2's representation, what is said? Area 2 has the same parameter, but on the base of 10,000. Then there is a shifting of base. So this shall not be forgotten. So therefore, what is exactly beta 2 now? Beta 2 is same as that of beta 1, but beta 1 is referred on the base of 2000. Then you can see how the author has presented it. 0.51 is the numerical value of beta 1 into the revised base to the old base. It is going to shift this 0.51 value to 2.55 pu megawatt per hertz, whatever the units we have mentioned here. The value is now got shifted to base of 10,000. So this is being done simply because otherwise what I would have done, this 0.01 converted to 10,000 base and 2 hertz per pu megawatt converted to 10,000 base keep added like this, D1, D2 plus 1 by R2. It is simpler. Whatever is the beta 1 value we have here, beta 1 value is on the base of 2000, shift that base to new base of 10,000. That's what is being done. Beta 1, whatever the value I got, into new base divided by old base, making it to be a shifted value on the new base of 10,000. That is beta 2. Now it is done. Rest of the work you can see on the page. It's so simple. So now you have a step change of load. What is the load change? 20 megawatt. Then 20 megawatt divided by 2000. 2000 being the reference of the system, divided by 2000 being 0.01 pu megawatt. Okay. Then when I make it 20,000, I mean 20 divided by 2000, 0.01 pu megawatt is the shift in load. Then steady state frequency deviation. What is the steady state frequency deviation equation? Minus delta PL1 divided by 1 by R1 plus D1 plus 1 by R2 plus D2. Nothing but minus delta PL1 divided by beta 1 plus beta. That's what is done here. Beta 1 and beta 2 in the denominator. Numerator is the step change in per unit. So 0.01 divided by these values lead you 0.003268 hertz, because it is directly in hertz. Why it is in hertz? I have conveyed you. Sum of the problem define delta omega or delta f in pu, because their calculation whatever went with the dimension you must see. Here it is megawatt per hertz. Here also megawatt per hertz. When I take a ratio, okay, what remains is hertz. Outcome of this is hertz. Hence it is hertz here. So that you might have observed some problems which you have discussed in the earlier class. They were mentioning you, or they were getting the numerical evaluation on per unit basis. That time we multiplied by the base frequency whatever was given, and we could get the change in frequency. That is what the change we have noticed. Then next question is the change in tie line power, delta P12, and we know that delta P12 is minus of delta P21, opposite to each other. Then what is this exactly? Minus. Now observe here, what was the equation? Hope you remember it. What was the equation for the power exchange among the corporation? When the load change in area 1 occur, delivered from area 2, it is delta PL1 minus delta PL1 into beta 2. Beta 2 means frequency composite response of area 2 divided by beta 1 plus beta 2. It is minus delta PL1 into beta 2 divided by beta 1 plus beta 2. So you have to remember the hardly 2 equations per derivation we have. So you should be very specific to use those equations as per the case study. So here it is minus delta PL1 into beta 2 divided by beta 1 plus beta 2. It stands as minus 0.003833 like this pu megawatt into 20, I mean into 2000. If you operate, you are going to get 16.67 megawatt with a minus sign. Note that frequency drop is only some percent of the calculated expense. This line you can omit off, because this is a relative question of another part of the problem which I have not disclosed to you. It means this is one of the problem which the another part of the problem was comparing the change in frequency with the governor, without the governor like concept was there. So this line is just a comparison. We can omit off this line. Our intention is to get in this problem frequency deviation and change in tie line power. This is how you can see here. Also note that this frequency support is accomplished by an added delivery of 16.67 megawatt from the larger area. It is the drawback of primary ALFC. It means if you do not have supplementary control, I am quite sure both the area will strive hard and the larger capacity area will contribute larger the megawatt for the disturbance whatever. So therefore 10,000 megawatt area is going to pump 16.67 megawatt from its location towards the area 1. This is to understand the primary ALFC's role itself. That's what, after having seen numerical problem, you will find whenever there is a problem in a certain area as a disturbance, how the disturbance is shared in proportion to capacity and characteristics from the interconnected operations perspective. The one which is having larger capacity will support larger in proportion. So this is not going to be an economical in view of the case studies. Hence, supplementary control will become very necessary. That's what we have to view into. Next, this was the problem. Already we revisited this problem. So I just take another problem or another content which we have not seen. I think you have seen this problem also. Let us move to another concept. When we have two areas interconnected to exchange a power, there comes some typical observation. Just we got to know that for a parallel operation of these corporation, whichever side is the disturbance due to load change, both the area will respond, start sharing the disturbance in proportion to their capacity and characteristics. On that basis, there are three observations made. So from the previous examples, whatever we have just see with the only primary loop, so that is what is the notice. Now supplementary control has become very necessary such that the area which experience a change in load should address it itself first. Then if it is not able to cope up, interconnected area need to respond for that secondarily. Therefore, in line with that, whenever there is a change in frequency in a certain area, for the parallel operation, both do experience that change in frequency. But who should respond for that? For that, the area caused the change in deviation should respond first. That's what is the tie line bias control we are trying to understand. So under the tie line bias control or frequency bias tie line control, we have three main headings. What are three headings? The delivery of power among the corporation can be of this mode: flat frequency base. It means flat frequency where control is to obtain constant frequency only. When one of the system of group of interconnected system respond to frequency change only, it cannot have control over the power flow in the interconnected tie lines. This is one of the remedy for the problems what we are finding. It means to say, whenever there is a disturbance, interconnected areas, all interconnected areas will respond for the change. That is the observation. Now we don't want to have that observation, that kind of action initiated from each corporation, we want to prohibit. Then what is that solution we want to apply? Flat frequency control we would like to practice. Then flat frequency control of interconnected systems means only certain identified systems only respond for change in frequency and rest will be on there. This system will not look for power delivery. It will not look for how much is the power flowing on the tie line. It will not monitor. It will monitor only frequency. Now you look back to the AGC. What is the objective of AGC? Automatic generation controller is simulated or installed in a power system to see to that active power balance and frequency is appropriately maintained. It has to do two objectives: active power balance as well as frequency to be at said. So now in this flat frequency, there is a compromise. What is the compromise? It is going to maintain flat frequency, whatever is said, but active power delivery from that generator, it is not going to concentrate. Rest of the systems are going to concentrate. This is a small deviation in the definition or observation when flat frequency technique is practiced. But this ensures frequency is maintained flat, but that machine's tie line power flow is not controlled. This is one method. The another method is when a system responds to tie line changes and changes in its generation to maintain the scheduled tie line interchange, it cannot respond to the frequency change. This is called flat tie line mode. This is flat frequency mode. This is flat tie line mode. Here the difference is exactly opposite what we discussed in the parameter number 1. Here frequency is not observed. Here only the delivery of megawatt is balanced. So change in frequency is due to change in megawatt only. Address the megawatt so that demand what is to be met through the tie line is balanced. Accordingly, frequency has to change, but that is not monitored. Only what is monitored is tie line power flow delivery must be appropriate as requested. That is called as flat tie line mode of operation. So the first one is looking only for the frequency, will not look at the tie line flow. The second method is look for the tie line power flow as a concentration. Frequency is not monitored. Both have its own, can say, pros and cons. Therefore, it is not acceptable in the power system to negotiate with either one or two. We want both of them as our required parameter. Hence, both of these methods have disadvantages. This is line mentioned here. So, combined control is utilized called as frequency bias control. So, this is the third way. Third mode is the combination of these two. For this example, if there is a drop in frequency, that is due to power flow mismatch only. While attaining the power flow mismatch appropriately by having additional generation, see to it that frequency of the system is also maintained in proper way. Then in this view, who has to respond in the particular first parameter? Only certain generators are only going to respond for the frequency change. In the second concept, only few of the or all of the generators are going to respond only for a flat delivery, and nobody will concentrate on frequency here. But it is an adverse phenomenon. Both should happen. In that view, if that is the decision, both should happen, then who should respond for the frequency control and who should respond for the megawatt balance? This become an issue, because we don't know all the time all the generator will not be in practice. Some of the generators were put off, some of the generators are on unit commitment, like that. So then those committed generators for a frequency control, committed generator for the Thailand flat mode may not be there in your system at the time of your operation. Then this cannot be fulfilled in an easy way. Then see a case study. Here a case is mentioned. When we have seen an isolated system, means individual system, an integral controller stabilizes the frequency deviation to 0. We have seen in case of ALFC, automatic load frequency controller, working only with the primary loop, which was sufficing only the mechanical substitute of power to the turbine, which would have taken the RPM of the turbine to the steady state, would have matched your megawatt requirement. But we have seen frequency of the line power was our requirement. Then that necessitated secondary control or supplementary control. That's what we are trying to recall here. That integral controller taken from the particular delta omega and fed back to the power set point. It means speed set point changer, that we call as ACE, area control error concept. That stabilized it means integral controller stabilizes that frequency deviation in that area. In case of two area system, as I have in the next slide, let us consider identical areas with the area 1 supplying certain 150 megawatt. I have here two area control. I have ALFC only with the primary loop, ALFC with both primary and secondary loop. Integral controller is taken. This is the integral of the error amplified with the gain and integrated, and that is fed as an input to control the set point of the governor. Governor's reference point is modified, so that modified governor reference point will act with the governor to control the input supplement to the turbine to see to it that the deviation is arrested to 0. That was not possible only with the primary loop, because set point was fixed here. It was fixed and it was not varied. Here it is a variation. Set point is altered by the frequency deviation using the integral controller in that path. So therefore, this is the primary part. This is the secondary part added to that. Now, if such an component, such an controller is there in both the areas, which two area control we have seen. See a small change here. There is a governor mechanism. There is a turbine mechanism. There is an area 1 with a D1 and deviation. Similarly, I have here governor in second area, turbine in second area, and area and response. Then it's deviation back, droop R2, droop R1. And this was the P reference. So I go back to primary control here. Only P reference here. This P reference, how you set it was discussed here. Before this, there is an integral controller taking care of deviation of the frequency of that area. So now we can see this is the point where delta P reference 1 I am speaking. Behind this I have integral controller KI1S, means this kind of representation. Similarly, behind this area 2, before the reference set point, who is going to set it out? It is the integral controller. To this, some input has to come. We will see what is that. So we understood that integral controller, which will change the set point of the governor, definitely makes the closed loop operation of the power system ALFC with a primary mechanical supplement, with a supplementary or a secondary, changing the P reference point for the governor to modulate within that range for the requirement. So therefore, the integral controller was inserted here. Now, for the integral controller, what is the input in this simplified diagram? Frequency deviation. Now you observe from this particular frequency deviation of area 1 and frequency deviation of area 2 having summed up, because these two are exchanging the power, interconnected operation. When we see, this was the view, delta P12 and delta P12 is the power exchange among these two areas. So once we have this, the interconnection and the power, means you can say the power computation from area 1, area 2 taken, and it is fed to the control system block C. That was the only loop we stopped. You will find this error is taken forward. This was not seen in the earlier discussion. We have seen this was just fed to the summing block here, that's all. That was the only attention we have paid there in the primary loop concept. When you have secondary loop concept in a complete model, this error now taken forward like a delta P12, and along with the particular composite frequency response of area beta 1, beta 2. Then here there is a summing. This become area control error. Today we are trying to see to that when you have interconnected operation with the frequency bias mode. Frequency bias mode means as and when there is a fall in frequency, mechanical supplement as well as electrical power generation has to take place to see to that frequency drop is addressed by the respective area only. How is that controller in area 1 respond for a drop in frequency in its area due to its load? This ACE comes into picture. Area control error of 1 makes it possible by shifting the P reference. Suppose there is a increase in load in area 2, definitely deviation in the frequency is noticed. Both will experience. That time, area 1 is not going to respond for the drop of frequency due to area 2 load. Area 2's ACE will make the set point change. You will see this once more I'll come back to this diagram. ACE of this area 2 will shift the reference point. Automatically, governors in this area try to adjust that drop in frequency back to steady. This is how this integral controller, which is instituted just behind the P reference point, obtain error from the area. It's called area control error, which is transforming the power and frequency error into a accountable state called as area control error number 1. Area control error for area 2, which is the delta P12, whatever we had in the earlier discussion without the supplementary loop. I go back and I'll convey what was there. This will be very convenient. Can you see this? Hope this slide is visible to you. Somebody reply.
Yes, sir.
This is only with the primary. Yeah, please. Thank you. This is only with the primary. The change in this diagram, I am trying to distinguish you. This deviation, frequency deviation, is caused by system or area number 1. There is a deviation in frequency resulted by area number 2. These two must be same because they are interconnected. That is the common frequency taken back to the primary part of that by droop and trying to work it out. And similarly, same delta omega 2 is taken back via the droop of area 2 generator and to work by the approach. Here you will find missing supplementary loop here. P reference is set. No one is going to modify this. These two are predefined set points. It means shifting of this I am speaking now. You have not seen any this power flow, which whatever the transaction happening among these two. This is fed as an input to block 1 and block 2. This is just delta P12. The tie line mismatch power or tie line change in tie line power flow is fed to this area and stopped here. This line is taken forward like this, and from the delta omega 1 delta omega 2 composite frequency response of area 1 is put as a block in the path and mixed with the delta P12 at the primary part of this. Install an integral controller that makes the complete ALFC of area 1. I go back. This power, which is called as a power flowing among the corporations, change in tie line power delivery, that is forwarded here. Okay. Then this delta omega 1 from the upper block through composite frequency response of area 1. What is that? 1 by R1 plus D1, beta 1. Beta 1 is taken and that is mixed with the delta P12 mixed. That become area control error, that is integrated, amplified and integrated as P reference 1. I am trying to speak about what is the meaning of delta P ref 1. Delta P ref 1 in case of supplementary control in a interconnected area means that is A's being transformed. A's area control error via the integral controller transformed as a shiftment. This is nothing but the shiftment from the controller. That controller takes the input of frequency deviation of that area via the composite frequency response bias and tie line power exchange mismatch that is being fed here. The same way here also. In case of area 2, frequency deviation of area 2 is taken via the beta 2. And it is summed up here with the power flow among the corporations that is transformed as A's of 2, area control error of 2, that is amplified and integrated to get delta P reference 2. I am trying to convey you how this delta P reference is modified by integral controller and feedback path. How this delta P reference 1 is obtained from integral controller and the feedback path. That is making this diagram revised as 2 area system with complete ALFC, not the primary, complete ALFC. So for that it require deviation as well as exchanged power among the corporation to be taken. That's what I am trying to convey here. You can see this diagram. You can see this was an extra loop here. Hope you are able to visualize my cursor. This is an beta 1 composite response of area 1 is extra line drawn here and taken to this summing block. Then similarly from this area beta 2 taken to summing block number 2 here. This was as usual 1 by R1, 1 by R2 were already there in the earlier discussion. So delta P reference 1, delta P they were the beginning marks for the primary control. Now complete ALFC will have the reference point shifter, reference point controller as integral controller, which will change this reference point 1 and 2 as required. For that to act, input must be there, stimulus. Stimulus for this integral controller is area control error of that area. That is computed as frequency deviation of that area like delta omega 1, which is when they are interconnected, there is no doubt delta omega 1 is delta omega 2 because of the parallel operation. But when we analyze individually, delta omega 1 is the frequency deviation noticed from the area 1 perspective is fed back via the composite frequency response, which is this beta 1. Beta 1 is what? 1 by R1 plus D1. This 1 by R1 is primary loop. This is called primary loop. Secondary loop is having a constant beta 1. This beta 1 is 1 by R1 plus D1. Through that path, deviation is fed here. Deviation through the beta and power mismatch, what you were feeding here, is again taken forward and fed here. What I am doing? frequency deviation through the beta 1 and mismatch power I am combining. That combined representation is called as area control area. We will see by the equation how it look like. The frequency deviation through the bias B1 and mismatch power delta P12 together called as area control error of 1. Similarly, when I take this arrow downward, it become the frequency deviation through beta 2 and mismatch power, transforming it as ace of 2, area 2. Then that is gain multiplied by a constant and integrated to give you change in reference point if required. It means this integral controller will respond if required. Otherwise, this will be always in stop condition. Stop means not changing the point. Point is static. If there exists a requirement, integral controller will change the reference point, else it will be static in mode. We say integral is off means for this point is not altered. If it is on means it is trying to modify this. That is the meaning of integral controller in action in steady state, like this way. So you got to know the change in diagram. This is called as complete ALFC for multi-area or two-area system, because I have taken only 2 areas. So this delta P12 is taken forward, mixed with the frequency bias and error to get ACE. This ACE is being taken now as stimulus for the controller, integral controller. Integral controller will definitely modify the reference point if required for the governor to function as required. This is the theory behind this. Let us go ahead slowly. This is initiated because only the primary control we have seen. Supplementary control, when internal controller was seen, stability of this frequency deviation and error coming down to 0 was visualized when integral controller is utilized. That concept is utilized here. Now, how this can be re-understood? What is the meaning of AS1, AS2? How these values are computed? So we can think a little forward here. Let's see. To develop such a control, what the control we are developing? We are developing a control, tie line bias control. We are not controlling flat frequency control. We are not developing flat tie line control. We are developing third type, which is called tie line bias mode. So both I want to address. I want to address drop in frequency as well as tie line power to be steady. Both I want to concentrate. That is our objective. If there is a change in frequency or a decrease in frequency, but net interchange power leaving the control area increases, the increase in load is outside the area. So I have to think here now. There are two we should note. If there is a decrease in frequency, why frequency decrease? Frequency decrease in an area because of its load in this area or outside the area. So, but net interchange power leaving the control area increases. The increase in load is outside the control area. I mean to say, decrease in frequency. Whenever I have an interconnected mode of operation, naturally, due to the second area's load, frequency, if there is a fall, both the area experience a drop in frequency in that perspective. If there is a decrease in frequency, but net interchange power leaving the control area increases, this is because of increase in load is outside the control area. We have to be very careful here. You have to imagine this statement very carefully. Imagine there are 2 areas, area 1, area 2 interconnected. I am speaking about area 1. Area 1 experience decrease in frequency. Area 1 was steady state earlier, and both were steady state earlier, you can imagine. Area 2 experienced a change in load. Because of that change in load, let us visualize there is a drop in frequency in area 2. As these two were interconnected in parallel, the first area is natural to experience a drop in frequency. That is the beginning of the statement. If there is a decrease in frequency in a area number 1, but net interchange power leaving the control area of 1 increases, area 1 start pumping more and more power. That is because of increase in the load is outside the control area. This area 1 is trying to pump more and more power to the neighbor area, because neighbor area is causing a deviation that is responded by area number 1. This is what the first statement. If there is a decrease in frequency and the net interchange power leaving the control area also decreases. See here, there is a decrease in frequency of a area 1, and net power exchange from area 1 to area 2 also decreases. Then what is the increase? What is the content of that? The increase in load is in the same area. We can bifurcate from the observation decrease in frequency of a particular area occur by two ways. One is due to its own load, there could be a drop in frequency. That's correct. There could be a drop in frequency due to somebody's load. That's what is highlighted here. These two parameters must be concerned in our design. One is drop in frequency of a certain interconnected area has to be perfectly classified as drop due to its own load or drop due to its neighbor load, because this is important. When I want to see drop in frequency in itself has to be addressed by itself. If the drop in frequency is because of neighbor has to control, not our area. That I want to distinguish by these two statements. Then let us look into the observation. We can similarly have same cases for increase in frequency. This we have seen by decrease of frequency. It may be increase of frequency also. We can arrive at a control scheme by noting that exchange of power among the areas delta P12, a small, infinitesimally small exchange of power between 1 and 2 is P12 minus P12 schedule. What is this? P12, what is flowing from 1 to 2, and what is expected to flow, scheduled 1 to 2. That's called mismatch power. So we can say actual power flow from 1 to 2 and scheduled power flow from 1 to 2. This difference is called infinitesimally small change in tie line power flow. Using this, we can write a control signal made up of tie line flow deviation added to frequency deviation weighted by a bias factor can be achieved as a desired function to be obtained. What is this? Just see this control area. Area control error of a interconnected area number 1 is the mismatch power what the areas are exchanging among themselves. Can you see here? This is the power exchange on tie lines of 1 and 2 interconnected, which is scheduled, which is really scheduled, and what is flowing. So mismatch is nothing but delta P12. Delta P12 plus its frequency bias with respect to deviation of that area beta 1 into delta omega. This equation we call as area control of 1. Similarly, when I write with respect to other area which is receiving power or pumping power towards number 1, which is ACE2, which is delta 1 to, now we opposite, delta P21 in plus B2 or beta 2 delta omega. So control signal we call as area control error. So this area control error solves our problem. Whatever the problem we had, flat frequency control, which is not desirable, flat tie line control, not desirable. What is desirable? The tie line frequency bias. The tie line power has to be flown if there is a definite change in frequency due to respective areas. Respective area generator need to respond for that. That is configured by ACE signal. So therefore, how this ACE functions? Let us see one more derivation, one more concept I have. We understood that this particular ACE is nothing but delta P12. What is the power being exchanged among the corporation, which was stopped here in the primary loop? We forwarded it. Then we are mixing it with the frequency deviation of that area with the composite frequency response of that area beta 1. We are transforming that as a meaningful equation ACE. ACE is now delta P12 plus delta omega 1 into B1. That is ACE1. What is ACE2? ACE2 is delta P12, nothing but delta P21. Delta P12, delta P1 are opposite. You can see that. Here is a minus, here is a plus. So it is being fed in the plus, it is being fed in the negative of that. Therefore, it is clear that delta P12 and delta P21 are opposite to each other. So therefore, it is fed here and it is mixed with the delta omega 2 with the beta 2 to get it as ACE2. So AS1, AS2 are the additional signal we have to generate from the system to see to it that P reference point control is done by an integral controller. So this kind of additional infrastructure, if we institute around this loop, that is nothing but a complete model of ALFC in a interconnected mode that is going to fulfill tie-line frequency bias control. That is going to fulfill tie-line frequency bias control, the third mode of requirement, which will address both frequency management as well as the megawatt exchange also being noticed by that. Both the parameters are addressed by the mode number 3. So that is being installed by an integral controller having ACE transformed as frequency set point changer. Let's see once again how this is understood still better. I have another way of representation. Tie-line bias control for 2 area. The persistent static frequency error is intolerable. So this is I have taken from Dr. Jagadishan's presentation slide, which is one of the power system operation control textbook presentation. I have picked it. So it's available on net. Okay. The persistent static frequency error is intolerable. Also, a persistent static error in tie-line power flow would mean one area would have to support the other on a steady state basis. When I have tie-line control, why we put the tie lines? To trade power, to exchange the power, to sell or to borrow. Therefore, there is a need of power in one area, the another need to support it by flowing or flooding it on a tie lines. For that, that could experience a fault also or disturbance also. For that, it should be ready to face the counter or face that such actions. In that basis, the static frequency deviations are intolerable because the system which is delivering power to the needy area also experience a disturbance when it is delivering the power. Therefore, that is intolerable. That is the meaning of which. So the control strategy to be utilized in such area is tie-line bias. You can see here, it's straight away highlighted. The control strategy of tie-line bias control is based upon the principle that the operating pool member must contribute their share to frequency control in addition to taking care of their own net interchange. This is the beautiful definition of tie-line bias control. The control strategy of tie-line bias control is based upon the principle that operating pool members must contribute their share to frequency control in addition to taking care of their own net interchange. This means that for 2 area system, a steady state, that is both delta F0 and delta P120 must be error-free 0. They must be 0. It means deviation should not be there. Then only steady state is obtained. In that perspective, what is being written? To achieve these objectives. Objective is to achieve the frequency deviation to 0 and the tie-line mismatch power to be addressed. Error must be there. There should not be any flow. There should be should not be any additional flow, not the flow, additional flow, because it has been addressed like that. So to achieve these, area control error for these areas consist of linear combination of frequency and tie-line error. This is the meaning of ACE. ACE become now mismatch, infinitesimally small mismatch of power among the interconnected area plus the frequency tie-line bias of that. So beta 1 of that area into deviation and delta P21 of that second area plus B2 into delta F. The same equation I referred here. The same equation I referred here from Dr. K. Umarao textbook. I referred this. This is by another presentation. So the speed changer command will thus be of sum of. So now the change in speed changer point is integral controller of delta P12 plus beta 1 delta F1 dt and another integral. It means it is written as a mathematical integration of the sum of the mismatches being taken as an input to the integral block. So these two, this is set point change. This is nothing but ACE is integrated. This ACE being delta P12 and feedback path integrated as delta Pref1, delta Pref2 respectively in area 1, area 2. That is mentioned here. In area 1, integral of error with the gain, integral of this error with the gain. That is reference to. This was not there in the primary control. Because of that, only both the area were responding for the change in megawatt. To address it, I will address, it will address, that another will come forward to address. That's what happened. So that is what Thailand frequency bias control is, the scientific way of addressing the change in frequency deviation and change in Thailand power. Therefore, this must be addressed by this way. Let us go ahead. Once we got to know that ACE is the best input or the stimulus for the integral controller in multi-area operated ALFC in particular second with the supplementary loop. Let us go ahead further to revisit ourselves. What is control area? We learned a periphery or a geographical location in which generation, load, everything is set up. From the common control center, signal emit and reach the respective destination. This geographical periphery, we call it as control area. From this control area, every corner of which signal from this central controller will reach and communicate for their action. Then we defined what is this control area's error, whether this area is in stable operation, having sufficient generation, having shortfall of generation, deficit generation. How do you come to know? Area's value called as ACE. So I'm trying to define what is ACE in real logic. ACE is actual power flowing out of the control area, like P1, P2, P3 shown here, minus what is scheduled to flow, actual schedule really flowing power, scheduled power mismatch plus 10, a gain of 10 and frequency bias beta into delta F. This is the combination of the ACE. This we have seen long back, but now you are able to understand what is the meaning of ACE. So ideally ACE must be 0. ACE will not be 0, but the controller will try to make ACE 0. If ACE is 0, what is the meaning? This particular area is meeting its requirement very effectively and balanced. ACE is 0 means it is having a sufficient generation. If ACE is a plus means this area is having surplus generation. If ACE is negative, this is having a deficit generation, need power to meet the requirement. On that basis, the steady state operation of this particular area is defined by ACE. So this kind of ACE parameter is visualized in this diagram. So ACE defines the need for the power here. Why do frequency deviation occur here? If you connect mathematically, frequency deviation occur because of the mismatch of megawatt. Why mismatch of megawatt has occurred? The primary controller did not manage it, even after having worked to the fullest controlling point, did not manage this to 0. Therefore, revision of reference point become inevitable. Revision of reference point would again make governor to re-energize with the additional operating point band, so it may reach the deviation to 0. Then who will do this reference point control? Some controller has to be there for that, which will automatically do this. That is done by integral controller. This integral controller act on an input which will shift the reference point. Then the input for the integral controller is area control error. This area control error, if I study, only think this upper half. Upper half is a control area. From this control area, measure actual power flowing out. And you know what has to flow out as a scheduled, and you know the deviation, you know the response of this area as beta. So this area's beta 1, this area's delta omega or delta F, together configured as ACE1. ACE1 refers to the status of this area, whether this area is in balance, in deficit of generation, in excess generation, that I can quantify by ACE. ACE is 0, integral control will not function. It means this is steady state in operation. If ACE is having a plus value, this area is having additional generation. If ACE is negative, this area is in need of generation supplement. In that way, ACE defines the controller's role, whether it has to be functioning or steady state like that. So we got to know the meaningful approach for ACE. So therefore, ACE define the controller's operating point. Hence, this was the integral of the feedbacks of mismatch power and frequency bias and with a gain of K1. Like this ACE was seen as a basic definition. Let us see how this can be understood. When I have ACE1, ACE2 by two equations, ACE1 being the mismatch power among the area 1 to tie line power mismatch, delta P1 to beta 1 delta omega, which was seen from this angle. This angle. This ACE I'm trying to write. This ACE1 is what? Delta P12 and delta omega and B1. This is the equation which was written here. Correct? ACE1 is delta P12 beta 1 delta omega. ACE2 is delta P21 plus beta 2 delta omega. These two equations we revise on this basis. You have seen the discussion. Why do frequency deviation decrease occur, increase occur? Then what is the action to be initiated on the basis of ACE using these two parameters is summarized here. What is the summary? Using ACE1, ACE2, same equation I picked here. Delta P12 plus beta 1 delta omega, delta P21 plus beta 2 delta omega. Both the equations are same. And we know beta 1, beta 2 are the composite frequency bias. D1 plus 1 by R1, D2 plus 1 by R2. As usual. Now use this table. Hope I am audible to you all. Hope I am audible to you all.
Yes, sir.
Okay, thank you. So just observe the use of this is and what is that decision to be taken in respect to areas. I have two areas interconnected and I have a supplementary control integral controller. ACE is configured. ACE makes a set point change. I was trying to explain. Now we will see when is that control increase, decrease command is situated. That's how on these two equation basis. Let's observe delta omega as one column. Delta P12, the power exchange among the area as one column. And load change. Delta PL1 is the load change. Here, if I go back and show you, delta PL1 is the load change here. Delta PL2 is the load change. Load change may occur in area 1, area 2, or in side by side both the areas. Whatever is the decision. Depending upon the case 1, case 2, case 3. Change may occur in any one of the area or in both the areas. In that view, change in load another column and control action. What is the outcome? What is that decision to be taken for the control area is put in this table as a study outcome. How is that? Just see. If delta omega is minus and delta P12 is minus, delta P12, delta omega, if these two are minus in observation, what is the meaning of that? Load change is increase in area 1 itself. So I made an arrow here. By arrow, what we can understand, if there is a increase in load of area 1, let's say increase in area load of 1, delta P1 is increasing, that is plus, which indicate that drop in frequency, that is frequency is negative, which is because this increase in this cause the minus value delta P12 is needed more and more from supplement. Delta P12 negative indicates loading more and more on this system. Delta PL1 if increases in area 1, which will hit the frequency to diminish, frequency drops. This will observed as need of power. Delta P12 is nothing but expectation of the power via tie line. Am I right or not? When there is an increase of load in area 1, when the frequency falls, somebody has to fulfill it. That is viewed as what is that requirement? Mismatch power is negative on this area, means needing supplement of power to address this change. So this indicates that there is a change in area 1 load only. Then who has to address this area 1's load? See the control action. Increase the generation area 1 itself. Increase the generation area 1. If delta omega minus delta P12 minus means the knowledge what we get from the control system is delta PL1 is increasing. Because of that, delta P12 is minus, delta omega is minus. When delta omega and delta P12 of interconnected areas are minus, both are minus, it is an inference that load in area 1 is increasing. If that is the scenario, only increase generation in area 1. We'll see it when I put in the ACE equation. I'll prove that ACE 1 only become commanding, ACE 2 goes 0 when this is the case study. Let us observe this. When delta omega is minus, delta P12 is also minus. The inference of this is increase in load of area 1 is the reason for that. For that, control action must be generate more and more power from the generating area 1 itself. Next is the second case. There could be a drop in frequency, but delta P12 is plus. What is the meaning of that? If delta P12 observed is plus and delta omega is minus, drop in frequency is natural because of load. Load is from which area? We'll understand from the direction of delta P12. If delta P12 is plus and delta omega is minus, there is an increased load in area 2. Who has to address this load? This load must be addressed by increase in area 2 generator only. Earlier in primary loop, both were responding. Now, ELFC with the supplementary loop, with the ACE logic, whichever is the area causing a change in load, that area only need to respond. That is an advantage of the current decision what we are taking. When there is a dip in frequency due to the plus symbol of the delta P12, nothing but change in load in area 2 causing the drop in frequency, area 2 generation only need to attend this. That's the meaning. Then if the frequency is superior, frequency is rising upward, rising up, and delta P12 is minus. Now this is due to suddenly drop in load of area 2. Just see here. Frequency is becoming very much superior with the observation delta P12 is minus. It indicates that whatever was the load in area 2, got reduced because of which superior frequency is viewed on the system. This is indicated by plus of delta omega minus of delta P12 necessitates to think that the declining load in the area 2. Then what is the control action? Decrease the generation in area 2. Generators of area 2 must be commanded, reduce the generation set point. That means when delta P12 decrease in area 2, naturally frequency become superior. We don't want to frequency to shoot beyond our 1 pu frequency. Then what is the action? Decrease the generation as the load decreases. That's the observation. Similarly, I have frequency can be very superior rising if there is a drop in PL1. If there was a PL1 load in the area 1 is diminishing down, that is noticed as superior frequency of the interconnector operation. If the frequency shift up is due to area 1 drop of load, then what I should do? Decrease the generation in area 1. See, I'm not touching at this time generator 2. When load in the area 1 is falling, I am addressing generators of area 1 only. Other way also true. We can see the first line. When the load in the area 1 is increasing, what is attended here? Increase the generation in area 1. What it is the meaning now? When both are minus, increase the load in generation 1 because of increased load. Look at the other side here. Both are plus and plus. This is a decrease of load, decrease the generation. Whatever is that, you see to that the ACE based tie line bias control such a way operate. The drop in frequency may be due to internal load or external load. If it is internal to the area, you have to definitely adjust the generation at its own. If decrease of frequency is due to neighbor's load, neighbor generator has to respond for that, not yourself. Area 1 need not do, area 2 is the request of frequency drop. That's why frequency control has to be done from other end. So other way it can be increase of frequency due to drop of second area's load, second area only decrease the load generation, and increase of frequency is due to drop of first area's load, first area's generator only need to decrease down. This is a very simple table. No need to worry much. You have to worry about the nature of the frequency deviation. Decreasing due to its own area generator need to be adjusted. Increasing is in its own decrease its own area generator. That's what we are quantifying 4 cases, minus, minus, plus, plus respectively, with the increased load, decreased load in that nature. So this is the outcome of the area frequency control. How it is being done? You can just see this page. This page is again a revisit of the page using the block diagram which is drawn. So delta P12 being the exchange of power among the connected areas, and which is projected forward with the ACE as an input to the controller at area 1, AS2 as an input to the integral controller in area 2. Appropriately, the change in set point of area 1, area 2 is done by integral controller. So now let us say how this ACE is really causing area 1 alone to respond, area 2 to respond when AS2 is not 0, and how it is being done. I was speaking here, when AS, there is a demand in area 1, only area 1 AS must be there, AS2 should not be there. I said it. How is that? Just see here. This is another view of the different by Wood and Uhlenberg textbook. Only this MS plus D, the transfer functions is represented by different. Rest all is very similar. Rest all is very similar. Another block diagram, book to book, a small change you will notice. Then you just see here. ACE, how it is being done. ACE signal in a generalized form written as ACE1 equal to K1 delta P12. Delta P12 with the gain of K1, delta P21 with the gain of K2, B2 or beta 2 delta omega beta as it is. It should be 0 actually. ACE of area 1 is 0, ACE of area 2 is 0. It indicates that both the areas are in steady state. Let us observe the frequency deviation delta omega. What is delta omega in an interconnected operation? Whenever there is a change in load in area 1, we have seen minus delta PL1 divided by beta 1 plus beta 2. This is what the derivation we got in the earlier interaction. When two areas are interconnected, certain change in load in area 1 is observed. What is the frequency deviation noticed by both the areas? Delta omega is change in load delta PL1 divided by 1 by R1 plus D1 plus 1 by R2 plus D2. This is what the equation we got. Then we too got another equation. The power exchanged among the corporation as mismatch power on the tie line, or the infinitesimally small power flow on the tie line was delta P12 equal to minus delta PL1 minus delta PL1 minus delta PL1 beta 2 divided by beta 1 plus beta 2. Just a minute, I'll be back here. Hope my slide is visible. Hope my slide is visible.
Yes, sir. Visible.
Yeah, I will stop after this slide. Hope my slide is visible. Delta omega I could get from interconnected operation. Delta P12 I get from interconnected operation. Then letting gain of area 1, area 2 as if equal to 1. Let's observe this interaction here. K1, K2 are the gains of integral controller in area 1, area 2. Let it be 1. And the area frequency composite response of 1, beta 1, beta 2, be beta 1, B1, beta 2, B2 like that. Some simplification has been done. Put over here. Let's see here. ACE1, how it is restructured. ACE1 is K1 delta P12, you can see, minus delta PL1 beta 1 plus beta 2 divided by beta 1 plus beta 2. So when I cancel this, what the ACE1 remains? This ACE1 comes with a numerical value minus delta PL1. It means what I am doing here, let us be very clear. Suppose there is a change in load in area 1 by delta PL1. Delta omega can be written as minus delta PL1 divided by beta 1 plus beta 2, whatever we have understood. And delta P12 as change in tie line power flow. letting K1, K2 for the simplicity 1 and beta 1, beta 2 as B1 and B2 respectively on this page. By substituting these in this equation, I'll be able to get AS1 as minus delta PL1 inside the bracket beta 1 plus beta 2 divided by beta 1, beta 2. When I cancel these two, what remain here is minus delta PL. What exactly I got is from these two equations. First equation quantified me AS1 as minus delta PL1. Let's take a second equation. AS2 K2 delta P21 plus B2 delta omega. B2 is put as beta 2 over here. Then I will get this as minus delta PL1. Let's see here. Minus beta 2 plus beta 2 divided by beta 1 plus beta 2. In the numerator, beta 2 cancel. What it results? 0. Then what do you mean by this? AS2 is 0. Why it is 0? There is a cancellation of terms in the equation. It resulted you 0. Ultimately for me, whenever there is a change in load in area 1, area 1's A's become equal to the change value. What was the change? Delta PL1. It means area 1 commanded for a change of address. Area 2 is commanded 0. What it would mean? AS2 went 0 means controller in the area 2, integral controller will not function. Integral controller is having 0 input, it is steady state, it is an off state. Integral controller in area 1 is having a stimulus of minus delta PL1. It is commanded to change the set point. It means when I have a bias factor beta 1, beta 2 like that, for a step change in area 1, only area control error of 1 is commanded with a delta PL1 for the integral controller. The second command AS2 naturally went 0. Then when I go back here, I go back and tell you this command is minus delta PL1, which is commanded on this integral controller. That will be a shift in delta PL1 over here. But about here, AS2 is 0. When it is 0, this is steady state. It is not going to respond. Now I will come back. Why AS1 is non-zero? The case study was there was a change in load in delta PL1. There was no change in delta PL2, steady state. It was carrying whatever the old load. There was an increased load in the area 1. Because of that, frequency deviation was experienced. This frequency deviation mixed as A's at the input. Because of the additional load, there was a floating load here, which was a delta P12 mismatch among the power flow between A and 1 and 2. That is a delta P12. Delta P12 and deviation whatever is noticed by this area as well as this area, both the areas are experiencing a change in frequency. But no one who is going to respond? Not the second. The first is only going to respond via this A is equal to non-zero, A is equal to 0. It means even though there is a change in frequency, this area is not going to respond for that change in frequency. That is made as A is 0. Don't respond. Don't change the set point. Keep spinning with the similar. This is non-zero will make the set point change over here so that governor will actuate further to see to it that arrest of this delta omega to 0. So this way, A's in area 1 make a controller to function to shift the reference point and make the error 0. This is how tie line bias control is done. So the second machine experience the delta omega 0 means error 0 very soon once area 1 respond for the changes being set in the speed point. This way, this particular reference point shifting is done by A's controller. A's of the area 1 become change in load of the area 1 and A's of the area 2 remain as usual. The other case study also same. Assume that there is a change in load in area 2. How do we mention this? Change in area 2. Frequency deviation is delta omega equal to, you can see here, delta PL2 divided by beta 1 plus beta 2. This delta P12 works out as delta PL2 beta 1 divided by beta 1 plus beta 2. That time it will be minus become plus at that time. It means when I consider change in load in area 2, delta PL2 and delta PL2 beta 1 divided by beta 1 plus beta 2 and use them in this equation. Now you may get similar answer like that. AS1 cancels with 0. Like this cancellation will take place in the numerator of AS1. This becomes 0. And AS2 non-zero, this turns out as delta PL2 in this position. It means to say AS2 is non-zero, AS1 is 0 at that time, which I have not concluded here. I have shown only one part of way where there is a change in load in area 1. As of that area is non-zero, it turns as the shift in load only. As of 2 naturally turns 0 because it should not respond for that. When I have a load change in area 2, I should experience non-zero AS2 and 0 in area 1. So naturally, when I go back to this screen, this AS turns 0 when there is a shift in load here. When there is a shift in load here, AS2 is non-zero. This is transforming as a change in reference point at this point by delta PL2 by the controller. This controller will respond if area 2 is going to cause a change in load and cause a change in frequency drop. At that time, area 1 is not going to respond for the change in frequency. This AC is caused 0. This is the beauty of interconnected operation. ACE value play a great role in energy control center. In the energy control center, computer controlled generation, ACE value of area 1, area 2, area 3 load center are usually used to transact the power among the corporations. Who is selling, who is buying, who all at what time, like that. ACE value define their transaction. ACE is a very important aspect of interconnected operation of systems in the real time. Therefore, I have just made you aware that how is that ACE makes the area to respond for a certain change in demand and change in frequency was just seen by the incorporation of supplementary control to the area's control system. So this made you very comfortable. Yes, there is a change in load of a certain area. Certain areas ACE is going to be get compelled for the action to be initiated. So this way, I just stop here. In the next class, we go ahead with the